would be the meaning of the rated values and examples or problems in this part. Rated power, it means that this is the maximum power that this machine can handle. So this is the manufacturer like nameplate for the machine. If I tell you that this machine rated power is 25 kVA, it is the maximum power that you can operate this machine. But based on your operation, you can, for example, operate this machine with 20 kVA only. You can operate this machine with 22, 23. Theoretically, any value up to 25. So yes, there is possibility actually that you have a rated value of 25 kVA, but in the question, the transformer, for example, or the device is just delivering or operated at less rated value. Okay, is this clear? So don't take the 25 kVA as the power for the transformer, for example, or the power that the transformer is delivering. It's the rated value. The transformer can deliver this or might deliver something else less than this value. Similarly, for the voltage, you can connect 440 in the input. This is the maximum. If you connect the 440, you expect to get at the output 220. But if you connect less than 440 in the input, what will happen? Well, the output will be also less because it's relation, the turns ratio relation. Okay? So it's rated values, they are important. But what's more important that you need to incorporate in your solution will be the information that you get later in the question. So we'll keep in mind the rated power, which is 25 kVA, also the rated voltage, primary and secondary. R1 and R2, they are the resistors in the primary and secondary, where the primary is 1, secondary is 2. X1, X2, also reactances in the primary and secondary. RC1, XM1, they are the RC and XM in the primary or secondary? Primary. You can see the one here, notation. So we know all the parameters. R1, X1, RC1, XM1 in the primary, R2, X2 in the secondary. We know all the rated values. So let's continue. The transformer delivers a 20 kilowatt at 0.8 power factor lagging to a load on the low voltage side with 220 across the load. So what do we have? We have actually transformer delivering to a load 20 kilowatt, 0.8 lagging with 220 volt across this load. So yes, the 222 is the rated value. So it's the same as the rated power that we are dealing with. But the power delivering to this load, is it the same as the rated power? Maybe. But this is the actual power that we are delivering to the load using the transformer. And this is the real power. This is the apparent power, which is okay, because we can change from the real to apparent power once we have also the power factor.
Doctor,
Yes.
I just need to check the current is lagging the voltage, right?
Yes, when we say power factor lagging, it means the current lagging the voltages. So again, we know all the data for parameters or all parameters for the equivalent circuit, not yet referred to primary or secondary. These are the original values for all the resistors and reactances. And we know the power and we know also the voltage at the secondary. The question is find the voltage, primary voltage. So what do you think, guys? How we can solve this problem?
Simplify the first circuits first.
First, yes.
Convert the primary to secondary.
That's correct. We need to draw the equivalent circuit. We know all the parameters, but we need to analyze the circuit. That's why we need to draw the equivalent circuit. And you have it here in the slide. And here we are using the exact equivalent circuit referred to primary. It doesn't mean that this is the only option that you have, because I didn't specify the type of the circuit. So you can use the equivalent referred to primary, the exact equivalent referred to primary, or the exact equivalent referred to secondary, or the approximate referred to primary, the approximate referred to secondary. Which approximate? The first one where you have RC and XM, right? Because they are given here. And you can see here, we can see here that the value for RC XM much larger than the remaining resistors. Yes.
Is it possible to have a different value for the low voltage side, which is 220 voltage?
Yes,
I mean, different than the rated value, what is given in the question.
I might specify the low voltage at the low side to be 210, for example.
What will be the difference?
The difference is that also the primary voltage will be less. It will not be 440 or around 440. So you take this as 210 and you solve the problem. That's it.
Got it.
Of course, ideally, if the voltage here 220 and this is ideal transformer, do we need to solve the problem? No. If it is ideal transformer, we know that the voltage here will be what? Am I right?
Yes.
Yes, because we know that the rated value 440 to 220, and this is transformer. So if it is ideal transformer and we know that this is 220, this will be 440. But it's not gonna be 440. Why? Because this is not.
It's not an ideal.
It's not ideal now. It's exact, meaning that we have some losses between the primary and secondary. So we expect this 440 or more or less. What do you think?
Less.
Yes.
More.
Less. No, more.
More 440. Why? Because we lose part of the power from the primary to secondary. Right? So there will be voltage drop on this. So yes, it's gonna be more. But let's do it and try to find out how much is the voltage at the primary. So yes, the first step was to draw the equivalent circuit, and we chose here the one exact equivalent circuit referred to primary. What do we know about the circuit? We know that our primary will be 0.16. Why? Because it's this value without any change. The X1 will be J.32. Do we change it? No, because it's already in the primary. RC will be 270. All of them ohms. XM will be 100. Without any change again. Why? Because all of them in the primary. And here we are referring to the primary. Now we come to the parameters in the secondary. First of all, how much the value of A?
2.
2. Why? Because it's voltage, rated voltage primary divided by rated voltage secondary, which is 440 divided by 220. Okay? So the value of A is 2. So what would be the value of this? It's going to be 4 which is A square multiplied by R2, which is 0.04. So it's 0.16. Do you see why it's 0.16?
Yes.
Again, it's 4A square multiplied by this. What about x2? It's 4 multiplied by 0.8, which is 0.32. So we know all the parameters here for this equivalent circuit. What do we know else in this circuit?
There is a load in the secondary.
Again?
There is a load.
Yes, we have first of all power 20 kilowatt and 0.8 lagging, and also the voltage. It's given for this circuit. We know the voltage at the secondary side, which is 440 volt. Why I said 440?
You multiply by A, which is 2.
Yes, the actual voltage is 220. We know it. But this is now the circuit referred to primary. So it's 440. Is it actually 440 here? No, it's 220. But referred to primary, changing the perspective of all parameters to be in the primary side, it's now 440. We need also to do one very important thing here, and keep this in mind. What do you think we need to do here?
Remove the resistance.
We have to consider the current to be divided by A.
No, we need to specify the reference. We did that, if you remember, before in the three-phase circuits, right? And this is AC circuit, not DC. So we need to set the angle to be 0 in the voltage. We can do it in the primary, or we can do it in the secondary, but we don't know the primary. What we know so far is the secondary. So yes, we set the angle to be 0 for the primary, for secondary voltage. Okay? So that's it. We are ready now to analyze this circuit. And it's easy. Once you reach this point, it's easy to analyze this circuit. Why? Because we have the voltage, we have the power, we have all the parameters, and we need to find this. So how we do this?
Assuming the current is minimum in the middle, so that we can add the impedances.
You can do this, but here we want to actually solve the circuit as is. No need to approximate.
We have the power, we can find the current.
Good point. We need to find this current, which is IS prime. So how we can find this current? So you know the voltage, just find the current. So this current will be, let's first of all think about this power. This power is equal VI cosine, right? We need to find the current. So what will be the current? The current will be...
It will be the power divided by the voltage times 0.8.
That's correct. 20K, which is the power, divided by 220, which is the voltage magnitude, divided the power factor, which is 0.8. Sorry, 440. Okay? Which makes sense. This is the power, this is the voltage, and this is the power factor. That's it. What we are missing here for the current?
The angle.
The angle.
The angle. Good. How we can specify the angle?
It's positive, which is lagging, and we have cosine inverse the power factor.
It's negative. Why negative?
Lagging.
Yes,
Isn't
you have to be careful. It's negative. Why? Because it's lagging the voltage. So it's lagging behind. So the voltage is 0. If the current is behind, it should be minus. Is it clear?
Yes.
Yes.
The angle is minus or the factor.
The power factor will never be minus because it's cosine something, so it is always positive. But the angle of the power factor can be positive or negative. It depends if it is lagging or leading. The angle of the current, it's much easier than thinking about the angle of the power factor. It can be positive or negative. So,
Doctor, in the inductive load, the angle will be positive or negative? With an
inductive is lagging power factor, so it's behind, yeah, negative for the current.
But I think in the lab we took that, we found that the angle is positive with inductive and negative with capacitive.
Well,
so how do we?
Which angle? Which angle? Because you cannot say that. Which angle? Is it the current, or the power factor angle, or the impedance itself?
The angle that we put in the cosine.
Yeah, it's the power factor. It's
Yes.
the power factor. This angle of the cosine is equal to the angle of voltage minus the angle of current. So yes, if this one is negative, what will happen to the overall angle here?
It will increase.
It will be positive.
Or positive, yes.
Why? Because this is 0 minus theta I. And this is the case of the inductance. So again, the relation, the power factor relation, when I say leading, it means that the current, the angle of the current is leading the angle of the voltage. So it's going to be positive because this is 0. If I say lagging, the angle of the current will be behind the angle of the voltage. So it's going to be negative. The angle of power factor will be opposite, of course, because it's theta V minus theta I. So for leading, it's going to be negative. For the power factor angle, negative. For lagging, it will be positive. Clear?
Yes, clear. But what's the angle that you were talking about?
The current angle. We're talking about the current here.
Okay. Clear.
Okay. Because we are trying to find what's the value for the current in the circuit, which is from the power equation. We can find the magnitude 20K divided by 440.8, but we need also to set the angle. So angle will be minus cosine inverse 0.8. Okay. Is it clear?
Yes, clear.
And this is the second important step that you have to do. After you set all the parameters and the voltage here, you need to find what's the current, which is also here. So what do we know now? We know the current, we know the voltage, we know all the parameters. And we need to find the voltage here. So it's easy. It's electric circuit. Nothing new. So how we can analyze this circuit to find the voltage here?
we do the KVL?
That's
then
correct.
we find the
We
voltage,
do
we find the current.
We write the KVL equation here. And the KVL equation will be, and I'm going to write it just for the first part. The KVL equation will be minus 440, 0, minus VE, where VE is the voltage here between the 2 points, plus, sorry, this is plus IS prime 0.16 plus J 0.32. So yes, VE will be 440 0 plus IS prime 0.16 plus J 0.32. And we know, of course, this, right?
Doctor, shouldn't we divide by A,
Where is, which A?
the current?
No. The current
prime.
here, the current here, which is IS prime, you find it from the values here. So forget about A, because A represents the, if you want to find the original current here for the secondary, yes, you multiply this by A. Okay?
Good. Okay.
But we are not talking about original currents here. We're talking about the new circuit referred to primary. Okay, so either you say that this value is IS divided by A is equal to this, or IS prime. Okay. So this is the KVL. So we can find this. Then what?
KVL on the left side.
Not yet.
You find the current.
You find the current first. You find the current here. You find the current here, which is, you add them. You add them together. This is the current. Then, since you have the current here, and also you have the current here, you can find the current here, right? KCL. Then you do the KVL. So I will try to number all the steps that you need to follow to solve or to find what's the primary voltage from the secondary voltage. 1, KVL here. 2, the current here. 3, the current here. 4, KCL to find the current, the total current for the excitation branch. 5 will be the current here, which is the addition of this current 4 and the original current IS prime. 6 will be KVL. So it's a series of KVL, KCL equations. 6 steps. Okay. Of course, I'm not considering the steps before where we find the current, for example, IS prime. That's it. You can find after that what is primary voltage.
Doctor,
Mm-hmm.
this is the exact method.
This is the exact. What will be the difference with the approximate? Let's assume that we started with the approximate circuit. Which is this. Let's assume that we started with this. Yeah. What will be the difference here? Well, we do the same thing. We find all the parameters. This one, this one, this one, and this one. The voltage also we find it. We calculate the current, similar to what we did before. Then what? We apply KVL, and that's it. It's only one step. That's why it's approximate circuit. Why? Because once we find the voltage here, it's the same as the voltage here, right?
Yes.
That's it. So yes, it's much easier, but you need to understand both of them and how to deal with both circuits. Yes, questions? What if the question is find what is this current? How many steps that you are gonna do in this equivalent circuit?
You do KCL. You find the current in the middle. which is in the voltage.
Yes. So we do similar to what we did before. So basically, this is 2, 3, 4, and after that 5. Someone actually might combine the two resistors here together. That's fine. You can do this.
Doctor,
Yes.
shouldn't we consider this current IB as the IS over A since we use the approximate method?
Again?
Shouldn't we consider IB as IS over A since we use the approximate method, since we combine the resistance? Because we say if the current in the middle is very low, the upper one will be in series, the resistance, the load.
That's correct, yes. That's correct. This current will be almost as this one. But without, if we don't ignore this, yes, we need to include it in the calculation. Otherwise, if you use this circuit, for example, it's one step, right?
Yes.
If the question is find the current, you just find this, which is the same as this. If the question is find the voltage, 1 kVL. Okay?
Director,
Mhm.
I think if we combine the two impedance in the middle, it will be, we will have less steps in the analysis.
Yes, if you combine this with this into one impedance, you just find the KVL 1, the current here 2, then KCL here 3. Yeah, that's fine. But you combine this also, so you can consider this as added step also.
Okay.
Doctor,
Mhm.
when do I need to use the approximate or the exact equivalent circuit in the
Well,
real?
if I don't mention anything to you, if I don't mention the type of the circuit, you use whatever you like. But if you have RC and XM given in the question, use them. So you have either this option, or these two options. If I don't give you RC and XM, if I said, for example, ignore RC and XM, you have only one option here, right? This or this. But if you have them as values similar to the example that we had today, or if I say that don't ignore RC and XM, you need to use either this, or the exact circuit. Do you refer to primary or refer to secondary? It's up to you, unless I specify, I say that use the refer to primary or refer to secondary circuit.
Doctor, even if you specify it, I can change it.
What do you mean?
If you are asking me about with refer to secondary parts, I can find the current in the secondary part, then I transform it to primary, isn't?
I didn't get the question exactly. So
I didn't know.
I'm talking about the representation itself. So you can represent the circuit, refer to primary or refer to secondary. Okay.
Okay.
So yes, it depends what's the requirement. If the requirements find the primary current, you find the equivalent circuit, and after that you find the primary current, for example. Or if it is this circuit, you find this current, you find the primary. To find the original values, this is the point here. You need to know exactly what's the relation between the original values and the represented values in this circuit. For example, here, if the question was what's the primary and voltage and current, the actual values will be the same as the values that you find here, right? For this circuit, if the question is find the primary voltage and the primary current, the actual values will not be the same as the values that you find in the circuit. Do you see the point here?
Yes.
The value of the current from the circuit will be AIP or IP prime.
Divided by.
VP, yeah, so you need to divide after that by A here to find the actual value, or multiply by A here to find the actual value of VP. Okay? Any other questions? Okay, so we're gonna continue here. Two different performance indicators that we need also to consider when we analyze equivalent circuits. It's not only analyze the circuit and find voltages, currents, but one very important indicator, it's called the voltage regulation. And we're gonna see this also with machines. Voltage regulation is a number that reflects how the voltage is changing from full load to no load condition. Let me define what do I mean by no load condition. No load condition, it's easy. We don't have any load connected to the transformer. Open circuit, nothing connected here. Full load condition, we have full load. We have load connected to the circuit. So the question here that we are trying to answer with this voltage regulation number, how much voltage drop you will have between the no load to full load? No load, it means that you have the best voltage that you can get. Because why? Because there is no current in the circuit. Open circuit, no load. So if you don't have any current from the input to the output, you expect less voltage drop. Full load, this is when you close this basically line and now you have current. And once you have current from the input to the output, yes, voltage will drop from the input to the output. So the difference between the no load and the full load condition, it's a performance indicator for the machine or for the transformer. Why? Because if you have large voltage drop, this is not good. You don't want the change to be high. You want the change to be as minimum as possible, meaning that if you have load or you don't have load, the voltage should be good or not changing that much. This is called the voltage regulation. At no load, when this one is open, what will be the value of the voltage here? It's Vs prime. And using the approximate circuit, as you can see, when this one is open circuit, this voltage will be the same as primary voltage. Do you agree? Yeah. If we have full load, meaning that we are closing this, is this gonna be the same as this one?
No.
No. We need to find what is this, which is basically through KVL, right? So the equation for the voltage regulation is voltage no load minus voltage full load divided by voltage full load. So it's a percentage. Voltage full no load, it's VP, which is like Vs prime at no load, which is the same as this, as we mentioned. Voltage full load is Vs prime as is. I mean, whatever voltage we have here at the load is gonna be Vs prime, which is the full load voltage. Whatever voltage we have at no load, it's the primary voltage. So in the previous example, if the question is find what is the voltage regulation, the one that it was given, the 440, is the Vs prime. The one that we solved, which is the voltage primary, which might be, for example, 450, it's here. Okay? And we are dealing only with magnitudes. So you don't include, for example, the angle here in the calculation, only magnitudes. So this is called the voltage regulation. And we're going to solve an example either today or tomorrow about the voltage regulation. The second also performance indicator that we need to know, it's called the efficiency. Efficiency, when we talk about efficiency, we're talking about the power. And we're not talking about any power, we're talking about real power, not reactive, not apparent power, real power only, or average power. And efficiency of any machine or device is the power output divided by power input. That's it. So you calculate the power output, you calculate the power input, and you just find the ratio or the average or the percentage. We know the relation also between the power output and power input through the losses. Power input is equal power output plus losses. Makes sense, right? Because part of the power input will be losses and the remaining will be power output. Okay? So yes, power input will go to satisfy the losses, and after that the power output. Losses, we have two losses here. The one, as I mentioned, it's average power. So it's the one in RC and the one in R equivalent. So you can calculate the one here in R equivalent through the current here. So it's I square, IS prime square, R equivalent. You can calculate the one in RC using the voltage here. So it's VP square divided by RC. The power output, similar to what we did before, either it's given or you can calculate the power output through the current and the voltage using this equation. The power input also you can calculate it using similar equation here, but with VP, IP cosine the angle between them. So it depends. It's not something new. What's new? It's the efficiency here. How to calculate the power? You know it from circuit one. Okay. So I will just discuss the question here, and maybe the solution we started next time. A 100 kVA. So this is the rated apparent power for the transformer. 8,277. So we have primary and secondary voltages. We have RP, XP, RC, R secondary, X secondary, XM. And you can see that the values here, they are very large values, 50K and 10K. The excitation branch, which is RC and XM, are given referred to high voltage side of the transformer. So what is the high voltage side of the transformer here? Is it the primary or secondary?
Primary.
Primary. So what he is saying here in this is that RC and XM, they are in the primary, not in the secondary. A, find the equivalent circuit of this transformer referred to the low voltage side. So is it referred to primary or secondary?
Primary.
Secondary.
Referred to secondary because the low voltage is secondary. So we need to refer the equivalent circuit to the secondary. So it's the opposite to the previous example. So now we need to divide the voltage by A, multiply the current by A, divide the resistance by A squared. And this is the answer here. Of course, A, we need to calculate A first. A will be 8,000 divided by 277. It's 28.88. So we divide this primary resistance by A square. It's going to be 0.006, which is this value. We divide, sorry, this is XP by A square. So it's 0.0072, which is this value. Also RC, we divided by A square, it's going to be 60. And XM divided by A square, it's going to be 12. This will be IP prime, which is AIB. This will be VP prime, which is VP divided by A. So we changed now the primary refit to secondary. We didn't change anything in the secondary side. Is it clear? Any question regarding this? So the second part, forget about the second part. It's not included in this course. Yes.
In the first part, we don't have to find A and I prime and V prime.
Not yet. This will be C.
Oh, okay.
So assume that this transformer is supplying rated load at 277 and 0.8 power factor lagging. There is a very important term here we used, which is called the rated load. So we don't have the power delivered, but he is saying that this transformer is given the rated load. So what is the rated load?
The one corresponds to the 8,400.
Yes, it's the power. The rated load or rated power, both of them, they are the same, which is the 100 kVA. So when I tell you or I say that the transformer is supplying rated load or rated power, it means that this 100 kVA is utilized fully with this voltage 277 and 0.8 power factor lagging. So now it's similar to the previous example, right? So what is the transformer input voltage? What is the voltage regulation? Is it clear the point of rated load or rated power? So the power will be 100 kVA at the output. So let's go through the solution here. As I mentioned, B, just skip this one, okay? I didn't remove it, I forgot, but it's not required. So now we form the approximate equivalent circuit. How we form the approximate equivalent circuit? Well, we have this exact. To form the equivalent, the approximate, we just add this in series with this. Okay? So we just add this to this, and that's it. This will be the approximate circuit. So now this is the approximate circuit. So you have the R equivalent, this is R equivalent, and this is X equivalent. And 60, J12, what will be the voltage here? This is the 277. What's the angle of this 277? Zero. Don't forget this. What's the power here? It's 100 kVA. And the power, the angle, is it 0.8?
0.85.
It's 0.85 lagging, yes. So we have here 0.85 lagging. And we need to find what is this, and after that voltage regulation, which is VP prime. So how we do this? Well, similar to what we did just in the previous example, but you have to be careful about one thing. This is not real power, this is apparent power. So to find the current, we divide this 100 kVA by only the voltage, not the power factor. You remember the equation for S? Right? VI. There's no cosine, there is no sine. After that, it's minus cosine inverse 0.85, which is this. So this is the current here, magnitude and phase. And we apply the KVL equation to find the voltage of the primary. So the voltage of the primary will be Vs plus the voltage drop, which is Is, multiplied by this. You have it here in numerical solution, and the answer will be 283 and the angle 0.4. How we can find the voltage regulation? Well, the equation voltage regulation is voltage no load divided by voltage full load divided by voltage full load multiplied by 100. So Vs is the 277. VP prime, which is the one that we calculated, 283, magnitude only. And that's it. This is the voltage regulation. 2.2%. So what's the meaning of 2.2%? the change between the full load and the no load condition is 2.2%, which is a good number. I'm going to continue, and maybe we go back and I explain a few things if required tomorrow. But we just have 2 parts left here, so a couple of minutes. D, what are the copper losses and core losses in the transformer under conditions of C? So the question here, what are the copper and core losses? So we have the equivalent circuit. The question here, what is the losses here? Copper. What is the losses here? Core. So how we can calculate the losses here, for example? What do you think?
I have the current.
Voltage times the
Yes,
current.
exactly. You have the current, which is this. You take the magnitude, 36.1 square, multiply by 0.11, 0.11. That's it. What about this?
V square over.
So you have the voltage, which is this one. Take the magnitude, square it, divided by the resistance here, which is the answer here, you see here. So the power losses will be 1430 and the power core is 1602.
Doctor, these are the losses of the active power. What about the reactant power?
We don't consider this in the efficiency. It's only about real power.
Oh, okay.
What about the power output? How we can find the power output? Well, we have S is 100 kVA, right? We have the power factor 0.85. So the power triangle, we can find the power output is equal 100 multiplied by 0.85. It's equal 85 kilowatt.
And subtract the losses.
Or subtract, we don't know the power input yet. But again, you all can also find what is the power input. That's why I said you can do whatever you want at that point. But you already know the power output or S output to be 100 kVA. And you know that the power factor 0.85. You can find the power output from the triangle, right? Why you are doing this? Because the last part is find what is the efficiency. How we can find the efficiency from the values that you have here? Efficiency, it's the power output divided by power input. What is the power input here?
The power output plus the losses.
Yes. So yes, we can find the power input and put it here. The power output, it's already 85 kilowatt here. This is the efficiency. Or someone actually might go to the circuit and say that I will find the power input from here, from this current, and this current, and this voltage. And the power input now will be VP prime, IP prime, and cosine the angle between them, right? You can do this, that's fine.
Doctor, what is the other way for the output? What is CU?
Again?
What is BCU?
It's the copper losses, which is basically the losses here and this resistor.
Okay. Okay.
So this is the answer for the efficiency, which is 96.6. So what we are saying here is that this transformer is 96.6 efficient, meaning that you lose only 3.4% for the losses. So we're done for today. You have this solution in the blackboard in the slide. So make sure that basically you understand the solution step by step. And try to solve the example that we discussed today and try to find the final answers for that example as a practice. Okay? So we'll see you tomorrow. So if you have any question, you can stay for the office hour. Otherwise, I will see you tomorrow. Assalamu alaikum.